For part 1, we are going to need the following items. We are going to use the 100 milliliter graduated cylinder. We are going to use the 10 ml graduated cylinder, the 10 ml graduated pipette. So for the pipette, we are gonna need the bulb, and then we are going to use a plastic vial with cap and a thermometer. The only chemical that we're going to use is deionized water. So in part 1, we have the goal of determining which one among these 3 pieces of glassware is the most accurate and precise to measure volumes of water. Okay, so what we're gonna do is we're going to measure 10 milliliters of water with each one of these 3 times. So 3 times with the 100 milliliter cylinder, 3 times with the 10 ml cylinder, and 3 times with the 10 ml graduated pipette. Then we are going to measure the mass, the weight of the volume of those 10 milliliters of water using a plastic vial. So in order to do that, we need to mass the plastic vial itself. So we need the weight of the plastic vial. So that's what I'm going to do now. Now we are going to use the balance, the scale. So when you need to measure the mass of anything that you're using in a lab, you want to make sure that the doors, see, the doors of the balance are completely closed. There are 3 doors, 1 on top and 1 and 2 at the sides. Then you want to press the 0T right in the middle. That is needed to zero the balance. Then you can open and slide the door, put your item, in this case the vial, close the door, wait for the numbers to stabilize, and then get your reading. So the vial that I am using right now weighs 6 grams, 0.828. And I'm gonna write this down. So now I have to measure 10 milliliters of water 3 times with the 10 milliliter graduated cylinder. So I am gonna take my deionized water, and I need to position myself in the correct way in order to be able to read the water level appropriately. So what I'm going to do is I am going to kneel, and do you see this? This is the 10. So I need to put my eyes at the level of the 10 milliliter marking straight, okay? So that when I put water, slowly, okay, so now I'm almost at 10 milliliter. Okay, so now I'm gonna show you something that is wrong when you read a volume in a cylinder or in a pipette, okay? So I'm gonna put these next to you, and can you see these? The bottom, this, so this is the meniscus. This is your reading. So right now, I'm not at 10 milliliters. Right now, I am slightly below 10 milliliters. So I need to add a little bit more water so that the bottom of the meniscus goes exactly to 10. So only if I kneel and I put my eyes in line with the meniscus, I am able to do this measurement correctly, okay? So you need to have your glassware laying, put in on a flat surface, and then your eyes straight to the volume that you want to read. So right now, I measured my 10 milliliters. I am gonna carefully transfer them, all of them. Make sure that you don't have any left in the vial. I am gonna close the vial, okay, with my 10 milliliters of water, and I'm gonna measure the weight of this water. So open the scale, weight. So right now the weight is 16.659, and I'm gonna write this down. 16.659. So at this point I can take my vial back and I can dispose of this water and repeat the measurement with these other 2 times. Okay, so now I disposed of the water, but as you can see, the vial is wet and still contains some droplets of water. So before I can reuse this, I need to dry it very carefully with a piece of paper. So I just put the paper inside, making sure that it touches the bottom. I am gonna turn it, and even outside, and voila, now it's dry and ready to be used again. So I'm gonna take my cylinder and again do my measurement, the second measurement. So I can go a little faster now. And I need to make sure that the meniscus is right at 10. Oops. Okay, so can you see this? The meniscus is right at 10. So now I am gonna take my dried vial and transfer everything inside it, shake it really well, cap the vial, and weight it again. So this time, wow, I have been quite precise. So this time the weight is 16.659, and I am going to write this down on a piece of paper. Okay? And again, I will take my water, I will dispose of, I will dry it, and measure it again. So now I'm gonna dry it again. Now it's dry, and I can measure again 10 milliliters. Can you see that? Okay. So now I am gonna put it here, shake it again, put the cap on, and weight it again. This time the weight is 16.614, which means that my eye hasn't been as good as it was with trial number 1 and trial number 2, because evidently the meniscus was slightly lower than before, but that's okay. So now I'm gonna dispose of this, and I'm gonna repeat the measurement using the 100 ml graduated cylinder. So now we are going to test the 100 milliliter graduated cylinder. As you can see, the 10 milliliter marking is right here. So I am gonna kneel again, and I am going to measure 10 milliliters. Okay, I'm almost there. Okay, there we go. I am gonna transfer these. Now that I measured 10 milliliters of water with the 100 milliliters graduated cylinder, I am gonna repeat the 3 measures using this time the 10 ml graduated pipette. So now I want to show you some specifics of this pipette. First of all, not every pipette is exactly the same. So for example, this is a glass pipette, Fisher brand, that is supposed to be very precise. And as you can see, it has the 0 marking right here, and then the 10 milliliters marking right here. Then we have this other brand. You can see that they're different, right? Okay, this other brand has the 0 marking right here, exactly like the other one, but there's no 10 milliliters marking, so it arrives at 9. This is because the tip of this pipette measures exactly 1 milliliter. So this is actually the 10 milliliter marking, okay? So can you see the difference between the two? Okay, so here with this one, where the 10 is not indicated, it means that the tip is 1 milliliter. Here, where the 10 is indicated, it means that the tip doesn't need to be counted. So now that I'm gonna measure 10 milliliters, what does it mean? It means that I will withdraw water from here up to here, up to the 0, and then when I'm gonna release the 10 milliliters, I will push the bulb so that the water goes down from here, and then here, and then here, and I am gonna stop right here, okay? If instead of stopping right here, I would have continued and delivered the entire volume contained in the tip, I wouldn't have measured 10 milliliters. I would have measured probably 11 or 10.7 milliliters. So I want this to be clear. When you use a pipette, you need to understand what you are using exactly and how the volumes are measured. So for this experiment, we are going to use not the serological pipette that you have in the trays, but this special glass pipette that is provided to you only for this experiment. Okay, so how do you use a pipette in general? You need a bulb that you need to put here, okay? You don't need to shove it inside, it just needs to be firm so that it doesn't fall, but not completely pushed down, okay? So the contact is needed because you need a sort of vacuum, otherwise when you suck the water or anything that you might want to measure, it's not gonna come out, it's not gonna come up properly. So now you're gonna squeeze the bulb, put the tip to the bottom of the beaker and then slightly release the pressure on the bulb, and I am going slightly above 0 because now I am going to put, see, the pipette vertical with the tip touching on the bottom, quickly removing the bulb and replacing with my thumb. So push out the bulb and quickly put your thumb. So now can you see where I am? See? The volume is here, okay? Now I am going to release the pressure of my thumb, okay? I am gonna sit on a stool because I need to look at the meniscus, okay? Turn it appropriately and release slightly the pressure with my thumb. As you can see, it's going slightly down. I am gonna show you very closely what is going to happen. See? Look at the volume here. So now I'm not gonna drop on the table. I have a small beaker here. So if I release slowly, the pressure on my thumb is going down, 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 down. If I put pressure, it will stop, okay? So now I'm gonna return here and do it again until the meniscus reaches the 0 marking. All right. So now I am at 0 right here, and when I'm gonna release the 10 milliliters in the vial, I will stop right here, okay? So let me go down. I can go a little bit faster until I arrive at 9 maybe, okay? Because then I will have to look at the meniscus at the 10 marking. It's going down, down, down. See, I'm not putting my thumb. Now when I arrive at 9, I am gonna put my thumb. There we go. So now I need to kneel, okay, and let it go. I am gonna turn it so you can see the 10, hopefully. Done. And I'm gonna put the rest in the beaker. So right now I am gonna cap my vial, okay? Slide the door of the scale, put my vial inside, close, and read. And the reading says 16.826. One thing that is really important for this experiment, as outlined in the lab manual, is that you will need to measure the temperature of the water that you're going to measure. And you need to measure the temperature of each single trial. So you have 3 trials for 3 pieces of glassware, so you are going to measure 9 water samples, and therefore you're going to measure 9 times the temperature. So this is a thermometer that you find in the lab, okay, so never touch this. And here you can see the on-off switch, and then Fahrenheit, centigrades, Celsius degrees. So here you see the on-off switch, and here you see the Fahrenheit Celsius degrees option. So we are doing science, therefore we are going to use Celsius degrees, okay? And we are going to turn on the thermometer. So right now it's saying that the room temperature is 21.2 degrees Celsius. But how do we know whether the thermometer is working properly? So what you will have to do is to put the tip of the thermometer in ice. You know that ice is 0 degrees Celsius, and therefore here it should display 0 degrees. If it doesn't, it means that the thermometer is not well calibrated, and therefore you need to take the difference into account. So let's say that if I put this into ice and this measures 2 degrees, then I will have to subtract these 2 degrees from my measures of my samples, okay? So I already calibrated this, and this works just fine. As you can see, the temperature of the room is, the reading of the temperature of the room has been stabilized. Now it's 20 degrees, 0.5. So now I'm gonna take my water sample, and I am going to put the thermometer right here, and I am going to read the temperature of my water, which is exactly room temperature. In this case, okay, please be considerate that these, the temperature of the labs change day by day and with seasons. So don't just assume that the temperature of your water is always the same of the room, okay? So you actually need to measure it every single time. So you measure the temperature of each of the 10 milliliters of water that you measured within the different trials, and you will note it on your notebook, because the temperature will actually be important for the calculation of the volume of your water. Okay, so now I reported all my data on the computer. So here I reported all the measurements that I made with the vial for the 10 milliliter graduated cylinder, 100 milliliter graduated cylinder, and 10 milliliter graduated pipette. Then this was the mass of the vial, so I subtracted the mass of the vial from this to get the weight of the water that I measured, okay? So this is the weight of the water alone for the 1, 2, 3 trials with the 3 pieces of glassware. Now, when I measured the temperature of the water, that turned out to be 20.1 degrees Celsius. So I went into the lab manual and I looked at this graph. So if you go under 20 degrees, you see that the density of water at 20 degrees Celsius is 0.9982. So I wrote that value here. Then I know that density is mass over volume, and therefore volume equals mass divided by density. So to get the real volume of water that I measured, I took the mass of the water and I divided every single one of these values by 0.9982, which is the density of water at 20 degrees. So these are the volumes that I measured actually with my 3 pieces of glassware. So then I calculated the average value for each set of measurements and the standard deviation. So as you can see, the the water, so the 10 milliliters of water that I measured appear here. Okay, so 10 milliliters, 10.01 milliliters is the volume that I measured on average using the 10 milliliters graduated pipette with a standard deviation of 0.01. Therefore, my measurement with the pipette is the most accurate and precise, because the average relates to the accuracy of a measurement, so how close my measures are to the real value, and the standard deviation relates to the precision of a measurement, so how close my measurements are to each other. So by comparison, then the second most accurate and precise device is the 10 milliliter cylinder, and the last one, the worst one, is the 100 ml graduated cylinder, as you probably imagined. Now we are going to move toward part 2. So the goal of part 2 is to learn how to graph your data and extract useful information from your graphs. Another thing that you're going to learn with part 2 is how to make a good graph. So what are the characteristics that make a graph a good graph? Now we are going to prepare 3 different solutions using sugar. So we need to choose 3 different weight percentages of sugar solutions. So first of all, what's a solution? A solution is not water. The solution is a solvent plus a solute. A solvent is the liquid in which the solute is dissolved, and the solute is the chemical that you are wanting to study. So in our specific example, a 10% sugar solution, weight, will be made of water as the solvent and 10% sugar as the solute. So I pre-labeled 3 beakers. I just used some tape and I wrote on the tape. So I will use these for the 10% sugar solution, these for the 20% sugar solution, and these for the 30% sugar solution. So how do you weigh a solid using a balance? First of all, you need your bottle of solid, which is the sugar. You need a spatula. Many students often do this mistake out of inexperience. So they use their spatula directly in the reagent bottle. No, this is a huge mistake, because if your spatula is dirty, even if you don't see it, it might be dirty with some other chemicals. If you put it directly in the bottle, you will contaminate the content, which you don't want. So the proper way is to equip yourself with a weigh book, drop a little bit of your chemical in the weigh book, put the bottle away, and use this as a dispenser for your chemical. Okay? So now I will close the door of the scale. You press the 0 to 0 the balance, and then you open the door, you put your beaker labeled with 10% inside, you close the door, and then you press 0 again, because you don't want to measure the weight of your beaker. You want to measure the weight of the sugar that you're gonna put inside. So at this point, I am gonna open the 2 side doors, So my right hand will be here and my left hand will be here with the weigh boat, okay? So I go inside and I put some of the sugar inside. For the 10% solution, I needed 3.5 grams. So I can just drop it, drop it, drop it, drop it, drop it. When I approach the 3.5, I'm gonna go very slow. So slower, slower. There we go. Let's see. Now I close so that air doesn't go inside and doesn't mess with the real weight of my sample. And I measure. Now this is 3.562 grams. Okay? So I need to take a little bit away. So I reopen. I do this, making sure that I don't put the spatula over the balance. I approach the weigh boat and I put it away. I close and I see how much it changed. It's not quite 3.5, it's 3.533, so I need to take some more away. Now I took too much, so I'm gonna open again and I'm gonna add just a tiny bit. So now I'm at 3.47, 3.49, I am so close. Okay, it's 3.504, so that's acceptable. So now we're gonna do the same thing with the 20%. So we need to weigh 3 grams of sugar. You open, you put the beaker inside, you close, and you zero. Now you reopen, you take the spatula with one hand, the weigh boat with the other, and you go on the other side so that you can work it well. And now you drop until you reach maybe 2.8, and when you are at 2.8 you start dropping slowly because you don't want to go over 3. So now I am at 2.982, 2.993, and then I close. 3.01, that's okay. So now I can take these away. Since I noticed that I spilled some sugar on the balance, I am gonna take this brush that you will find right in front of the scale, and I am gonna clean so that the next user, which might be you, finds the scale very, very clean and doesn't risk contamination. So once you're done, you close and you put the brush back. So now, to finish my solution, I need to take the water, which temperature I measured earlier, and I already told you that it was 20.1 degrees. Remember that for 10%, I needed 13.52 milliliters of water. Now, our pipette measures up to 10, so I'm gonna divide this measure in two. One of 10 milliliters and the other one of 3.52. So, I'm gonna squeeze, put it here, it goes up, 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 and use my thumb to bring it to 0. Look at the meniscus to be precise. There you go. And now drop it to here, up to 10. Remember that the tip of this pipette, it doesn't contain the volume that we want. So we need to stop at 10, okay? Very carefully, almost there, almost there. There you go, stop. So now this is ready, and I just need to add 3.52 milliliters more. See, this is graduated, and each small line corresponds to 0.1. I need to arrive here, which is the 0.5 is here, right in the middle between the two integers. So now I need 3.5 3.5, 1, 2, 3, 1, 2, 3 milliliters, 0.5, and a tiny bit more to account for the 2, 3.52. Okay, so I go higher, I take down the bulb, I use my thumb, and I go to the mark that I determine to be the one I need. There we go. Okay, so now again, drop up to the 10 mark. There we go. Oh, so now I am gonna do the same thing for the 20% solution and the 30% solution. Now that I added my solvent, water, to the sugar and I made my solutions, I noticed that some sugar is on the bottom. It didn't completely dissolve. This is the 10%. This is the 2, which I shaked a little bit, so now it's better. And this is the 30%, which I shaked. Now, to make things easier, I decided to use a stirrer. So I'm gonna put a magnetic stirrer here, and I am going to start stirring it. Don't go too wild with the speed, just enough that the solution is completely clear. There's still some sugar on the bottom, so I'm gonna stir it some more. That should be enough. I am going to use one of these to take these away. I am gonna dry these, and I'm gonna do the same with the 20 and then with the 30 until they are completely clear like this. This is really important because if the sugar is not completely dissolved, the concentration of the sugar in the solution will not be the one that you wanted. At this point, the lab manual, the experiment, says that you need to use the 10 milliliter graduated cylinder to measure 10 milliliters of your solutions, the ones that you just made, and these. You need to transfer them in a plastic vial and measure how much the 10 milliliters of your solutions weigh. I understand that this might be puzzling because we determined in part 1 that the graduated pipette is the most accurate and precise tool to liquid measures. That is true, and in fact, in principle, in theory, this is the one that we should use. However, sugar solutions are dense and sticky. The more dense they are, the stickier they are. Therefore, if you had to use the pipette, especially at higher percentages, for example, the 30%, the result will be that much of your solution will be stuck on the inside of your pipette, and you will not deliver the entire 10 milliliters, which would impair your measurements and your investigation on the density of the sugar solutions. So, although this is the most accurate and precise, for practice reasons, we need to use these to measure the 10 ml. Now that we established why we are using these and not the pipette, it's time to measure 10 milliliters of each solution using the graduated cylinder. So now I am going to kneel and very carefully drop the 10% solution inside the cylinder up to the 10 milliliters mark. Very carefully, you don't want to go higher than 10. So the meniscus is right at 10 right now. So now I can take these. Remember that we already know the weight of the plastic vial with its cap. I am gonna drop it entirely here. Make sure that nothing remains in the cylinder. There we go. So now I can cap it go to the balance and measure its weight. And then do the same thing for the 20% and the 30%. Now I'm gonna do it, and then I will show you the data. Okay, so here I made a few calculations. The lab manual calls for 15 grams of solution. Remember that 15 grams doesn't mean 15 milliliters, because density plays a big role in how much volume corresponds to a certain amount of mass of solution, okay? So as I said, the solution is made by a solvent, water in our case, plus a solute, sugar in our case. So in my case, I wanted to prepare 3 solutions. I have an example for 4 solutions, but I'm gonna make only 3 of those. So 10% sugar, 20% sugar, 30% sugar. This is an example calculation. So 10% sugar weight by weight means that in these 15 grams of solution that I need to make, 10% needs to be sugar. So if I multiply 15 grams times 0.1, 10%, I will get that I need to weigh 1.5 grams of sugar. So for 20% sugar solution, I will need to weigh 3 grams of sugar. For 30% solution, I will need to weigh 4.5 grams of sugar. Then I just need to subtract the sugar mass from the solution mass to find how much mass of water I need, okay? Remember that the density, that the volume of the water is related to the mass through the density. Density equal mass versus volume, and therefore volume equals mass divided by density. I measured the temperature of my water, which is 20.1 Celsius. The density of water at 20 degrees is 0.9982, and therefore 13.5 grams of water correspond to 13.52 milliliters of water, and so on for all the other amounts. Okay, so now what I'm gonna do is I will weigh first 1.5 grams of sugar, and then I will mix it with 13.5 grams of water, which is 13.52 milliliters. So I will mass the sugar with the balance, and I will take 13.52 milliliters using the tool that I determined in part 1 to be the most accurate and precise, which is the pipette. Okay, so here I have the weight of the 10 milliliters of 0% sugar, 10% sugar, 20% sugar, and 30% sugar with the vial and without the vial. Now, the experiment, the lab manual wants you to calculate the density of these solutions, okay? Just taking the weight divided by the volume, so these divided by 10 and so on. So you will have on your x-axis the concentration of your solution, and on the y-axis the density of the solution. Then you make a plot, and you need to make sure that you add a title that is meaningful, so that who doesn't know what you did immediately understands what the graph is representing. So in this case, density of sugar solutions. Then you need to label the axis. So on the x we have the concentration of the solution, and you need to say solution concentration and the unit that you used, the percent weight. On the y-axis, you have the density of solution and its unit, grams over milliliters. Finally, you fit your data with an equation that best represents your numbers. So in this case, it's a linear regression line, and this is the equation of the best fit. So y, the density, equals 0.375x concentration plus 0.979, which is the intercept. So the value of y at the zero value of x. And then you have the r square, which is in this case 0.0995. So the r square represents how good the fit is. So how good is the equation that you choose to fit your data. The closest to 1, the best, the fitting. So right now I got 0.995, so it's pretty good because it's almost 1. A 0.7 will be so and so, 0.5 is really bad, okay? So what does this graph tells you? That the density of sugar solutions, at least from 0 to 30%, increases linearly as the concentration of the solution increases, okay? So that's how you represent your data, with a good title of the graph, the titles of the axes, what they represent, with their units, the equation of the best fit, and the r square. One more piece of information: what do you put on the x-axis and what do you put on the y-axis? So on the y-axis, you put the dependent variable. So that variable that varies with the values of the x. And therefore the x is called independent variable because that's a direct measure that you made, okay?